Today's going to be pretty cool. We're going to introduce a bunch of topics that we're going to circle back on. Namely, we're going to dig into the solar system for the first time, really get into it. I know we did a very light speed exploration of the whole solar system in the first class. We're going to get into a little bit more detail today, and then in the subsequent weeks, we're going to look at each piece of the solar system and give it its own due time. First, though, we need to finish up with the telescopes. We didn't make it into the non-optical scopes. And they're worth mentioning. They're kind of cool, but they, in some sense, are quite different from your typical light telescopes. So we'll go over those real quick. And then a little solar system tour. And then finally, I want to hope that we'll have time to talk about the origins of the solar system, which is really quite an interesting story that's still in progress. It seems that today the origin story that is most popular, although I don't think it's totally popular with anyone, but it is the one that we've settled on, is actually a model that was developed in the 1700s, and then it was abandoned for about 300 years, and people wildly tried on all sorts of different models in the mid-20th, throughout the 20th century, and then came back to the 1700s model in the 70s, in the late 70s. So it's quite a story of how we've come to think about it. And there's serious problems with the model that we have today, and there's been all sorts of attempts to resolve them, and we're not there yet. So it's an open story, which is kind of cool. And honestly, that's the coolest part of this whole field of astronomy in general. There's just so much left to do if anybody wants to get involved in it. All right. Let's wrap up telescopes. So the last thing that we were talking about were these giant optical scopes that were being forged in the early 20th century. A lot of these scopes were actually made by amateur astronomers, which is pretty cool. I don't think I totally got into that story, but a number of these Harvard Observatory, this is Harvard Observatory, Harvard College Observatory in the 1800s, and a number of these lenses were actually fashioned by amateurs and then donated to Harvard, and then they dragged them all over the country. They were trying to find a good place where there wasn't atmospheric interference, and they tried to take it to, I think, out to Long's Peak, somewhere at 14,000 feet in the Rocky Mountains. They quickly discovered that the weather there was abominable. And so they ended up traveling all the way down to South America and finding a place in Chile to set up shop. And they're still there today. But they carted all of these homemade telescopes down there, and it's quite a saga. Okay, so beyond optical telescopes, there's a lot of information, a lot of light coming in that isn't optical. What I mean is it's higher energy or lower energy. It's radio waves, it's X-rays, it's gamma rays. And if you recall back to last week, there's this whole spectrum of light, of electromagnetic radiation that spans a wide swath of wavelengths. And most of them don't make it down to us here on Earth. And so these telescopes, for the most part, with the exception of radio telescopes, there is a small atmospheric window for radio waves. But most of these telescopes have to be installed outside of our atmosphere. So these are the orbiting satellite telescopes, the Hubbles and the James Webbs and so forth. And as you can see, so this is a picture from your textbook, which is kind of cool. If you just look in the optical here, which is on the far left, you don't get a ton of information here, and I believe we're looking at a piece of Orion here, yeah. But when you look at it in X-rays, you start to see a whole new level of information out of it, and then the same thing goes for infrared, which is over here on the far right. And this is because infrared is giving us information about how warm something is. So even if something's not giving off a lot of light, like, say, a dead, dying star or a recently cooled planet, we still can get infrared information from it. Getting infrared information is a nightmare, of course, because you have to have a really cold telescope. Otherwise, the heat from the scope is going to show up when you hit the detector, when the light hits the detector. Because infrared is essentially heat. It's essentially detecting heat. It's a thermal emission. So when the atoms vibrate in a particular way, in a heat-related fashion, they give off thermal light. This is called infrared. So today, we can see a lot of processes require us to look in different wavelengths. And this is looking at the same celestial cluster across all of the different wavelengths. What do I want to say about this? Radio waves are quite interesting. Let's see which one. Okay, on the upper left-hand side. So there's a number of ways that radio waves are generated, but it has to do with these large-scale interactions of the atoms in the atmospheres of these big bodies, right? So I think we have to take a little bit of an aside to talk about electricity and ionization. And maybe some of you have encountered these ideas in your science classes so far. Many of you haven't. There's a lot of non-science people in here too. So, and honestly, the people who have taken the science stuff, it's probably worth rethinking about it a little bit, because a lot of the atoms that are out there beyond the atmosphere of a planet exist in this form which we call ionized, which is a strange concept. And one way to think about it, and the way that most textbooks think about it, is that the electrons, which are some constituent part of the atom, have been stripped from the nuclei of the atoms. And so there's something like a sea of electrons amidst the cores of the atoms, right? And I think this is totally appropriate. It makes a lot of schematic sense. But another way to think about it is that you have this. The atom has a shell, which we call the electron, right? It's the surface, the outer surface of the atom. In a metal, those shells are essentially all merged into one, so that the electrical motion inside of the shell can conduct from atom to atom because they're in contact. And I think that a reasonable way to think about ionized molecules in space is that they're actually the pressure is so low that their shells are wildly expanded, such that they're also able to be in continuous contact with one another. So it's like these really thinned out, blown up atoms out there that are able to conduct electricity. And electricity is a weird thing too, because you probably learn in high school that electricity is the flow of electrons. But that doesn't really work out. It doesn't really seem to make sense, because the electrons don't travel fast enough to conduct at the speeds that we know that conduction is possible. So in reality, it's more of like a momentum transfer. Like if you have two things that are touching one another, especially if they're really stiff, you can conduct, like if I hit the end of this table, the impulse will come out the other end almost immediately. And so there's something similar going on with electricity amongst the shells of the atoms as they contact one another. They're able to drive this impulse very quickly across a distance. And electricity turns out to be one particular motion of the shell of the atom. And the shells of these atoms can get really complicated. They're not always just simple hydrogen, although there's a lot of that out in space too. So a particular form, as you excite atoms, we talked about this a bit before, the atoms are changing shape. Their shells are changing shape, and they give off light, which is commensurate with the shape change of those atoms. And as these really complex currents, and you can really think of them as rivers of motion in the atmospheres of these planets, or in some of these nebula, as these molecules are traveling and pushing on one another, they generate wild currents, which are very thinned out. They don't seem to be necessarily at any local point a very large current. You're not going to hurt yourself. But en masse, when you put gazillions of atoms together, you can get substantial electromagnetism. And so magnetism is essentially just the other side of that electrical phenomena. If you think about electricity as being this directional propagation of that momentum across a chain of atoms, then magnetism is just the lateral effect of that. So it's essentially the sideways, the magnetic force is always at a 90-degree angle to the electric force. So if we're pushing this way, and that's our electric force, then the magnetism is going to rotate this way and affect things off to the side. So all of these things conspire to make really amazing structures out of these simple molecules in space, and that's how we get these beautiful nebula and so forth, and really the beautiful aurora and electrical phenomena that we see in the atmospheres of places like Jupiter and even in our own atmosphere. This is all a long way of saying that these electromagnetic structures that appear in these gas clouds and atmosphere and so forth, they're capable of generating a particular kind of radiation, which we call radio waves. Because radio waves are really long, right? If you want to actually make an antenna to generate radio waves, you will have to scale the size of that antenna with some geometric ratio to the waves that you want to produce. In other words, it seems to be a group effect. Whereas like a gas is going to give off a single frequency, radio waves are atoms acting in concert, many atoms acting in concert to give off a big wave altogether. So they're more like a stadium wave, whereas like the individual gases are giving off their own vibrations independently. Yeah. Yeah, so those are primarily radio waves as well. And there's some infrared radiation as well. I mean, everything gives off radiation. That's kind of worth considering. It's pretty much impossible unless you cool something to absolute zero. In other words, such that the atom wouldn't be moving, which seems to be next to impossible, Every once in a while you see like a scientific report that people are achieving, or very close, within 0.00001 Kelvin of absolute zero or something. You can't stop motion, right? So as long as the atoms are moving, they're going to be giving off some sort of light. And of course, this really gets you thinking about, again, what is light? It's some sort of conversation that's happening with the atoms, and it doesn't seem like you're able to completely isolate an atom from the rest of them. And so as long as you can't isolate the atom from the rest of them, there's going to be some sort of light happening, some sort of radiation. So these radio waves are a really good source of information about these large-scale structures because they tend to be the ones that they have enough atoms to give off these big collective waves amongst one another, which is pretty cool. All right. Not much to say about this. This is obviously a picture of infrared radiation, right? It's thermal, so you can see through things that would otherwise shield it. Let's talk a little bit about radio astronomy. So this is kind of a cool story. Radio's waves were obviously being harnessed for communication purposes. This is Carl Jansky. I think this is in the 30s. Yeah. And Jansky was actually working, I believe, for Bell. He was trying to establish some long-range communication through these radio technologies. And he noticed something very strange. There was this noise that kept popping up in his detectors every day. But what was strange was that it came in about 4 minutes earlier on each successive day. And he was like, this is very strange, because he thought at first it had something to do with the sun, but it was coming up before sunrise every day. And so he was just talking one day with a friend who was an astrophysicist, or an astronomer perhaps. And his friend pointed out that the sidereal day actually corresponded to this interval, because the sidereal, my wife corrected me last night. Sidereal, that's the correct way to say it. It's sidereal, excuse me. All right, so the sidereal day is actually 4 minutes shorter. And why is that? Well, so the sidereal day is actually the true rotation of the Earth, right? When the Earth makes a 360-degree rotation. But what's interesting is that the Earth itself is moving around the sun, right? And so it has to turn a little bit more to face the sun every day. And this makes the solar day, which we would generally care most about on Earth, just a little bit longer. And so his source, he reasoned, must have been coming from some fixed star because that position didn't seem to correspond exactly to the day. And that was it. That was the idea that, hey, we can get radio information from the stars, which is a pretty cool story of discovery. Today, the best way to do this is to put up these large arrays of radio telescopes. And they use this in order to improve the resolution. So when you string a bunch of radio telescopes together, I'll come back to that. When you string a bunch of radio telescopes together, you actually have the effect of having a single telescope that's the same size as the spread that you've laid out, which is quite incredible. So you can get a really wide resolution with these scopes. So like 2 telescopes that are separated by a kilometer is the same as 1 dish that's a kilometer wide, which is pretty cool. I'm going to go back and just show you this. This is a cool picture. You can actually, this is looking at the center of our galaxy, but you can see these little poofs now and then. And it's thought that these remnants, which you can't see in the optical, are actually the remnants of exploded stars of supernova, which we'll get to later in the course. All right. So they have these very large arrays, like many telescopes, all stationed together. This is in Chile, not too far from the original Harvard project. All right. So one of the best arrays that we have today. This is worth pointing out too. You can see with great resolution, they can actually resolve something like 0.0001 arc seconds. But the truth of that is that things are so far away that even that really high resolution only gets you something like 10 AUs at the center of the galaxy. So that's an AU, remember, is the distance from us to the sun. And that's about the pixelated resolution that you get when you look at the center of the galaxy, is about that distance. So you're not going to see anything smaller than what's between us, 10 times our distance to the sun. And this is, of course, why people are really anxious to get telescopes out past the atmosphere, out into space. Of course, making a huge array in space is going to be a nightmare. And we'll talk about the ideas of how to pull that off in a second. There's also these things called radar telescopes, which basically work like the way that the cops check your speed on the highway, right? They shine a laser at you, and they look for the reflections coming back, and they can gauge based on the compression of those waves as they reflect how fast you're going. This is quite interesting. The speed of light is fixed. We talked about that. But the wave properties are not. And so there happens to be compression of waves in the direction of propagation and the stretching as it moves away. And there's a lot of information we can get from that. We'll talk about it more either in this course or next semester. So some of our best hopes are this is a picture from Hubble, where we're able to see quite far. We don't have the atmospheric interference, although it's not clear that there's not atmospheric interference from all the star systems. And then one last thing I want to say about telescopes is about X-ray telescopes, because this one could really stump you if you think about it, because obviously X-rays are used to see into things. So how do you catch them and focus them and look at them with a detector? This has turned out to be no small challenge. And the principle behind X-ray telescopes has to do with this very convenient property of total external reflection, where you can actually you can reflect X-rays as long as most of the momentum is carried forward. So if you keep the angle of reflection below something like 3 degrees, don't quote me on that, some very low angle, you're able to actually skip them, like skipping stones off of a pond. You're actually able to skip these rays. You go beyond that, and the X-rays will penetrate most materials. So they basically just set up this array of very low-angle mirrors, and they construct these mirrors out of some very high-density metal. And they use gold and iridium. Okay, so I wrote it down. So the critical angle is 2.4 degrees that you can't exceed. So they have these large focusing arrays, and they'll fix these down into the detector. And these are, of course, all space-bound telescopes because X-rays are not penetrating, for the most part, into our atmosphere. If they did, we'd all be getting cooked. It wouldn't be good for our DNA. And so what's going to happen in the future with telescopes? This is perhaps an interesting story. Had a movie here. It's not playing. What are you going to do? Oh, here we go. You going to play? So the future of telescopes, and I think the future of space travel and space craft in general, is really going to come down to self-assembling structures. Because the trickiest part of getting something built in space is getting it through the atmosphere. And of course, the easiest way to get something through the atmosphere is to have a pointy little tube that you can cut through the atmosphere with. And once you get up there, then you can unpack whatever massive objects you'd like to build. And so a lot of the industry research around the construction of new spacecraft and telescopes has to do with how to get them to fold up. And there's a lot of really cool ideas out there about how to get the structures to self-assemble. You know, nature is really good at this already, right? Plants do this. You know, the flowers, the way they unfold and they pack actually, and the way that they're actuated by the moisture is really something incredible too. So I think there will be not only a lot of folding and self-assembling, but also a lot of consideration of how to energize that process once you get up there. This is just like an artist's conception of what this might look like in the future, self-assembling habitats and so forth. They're also dealing with this problem of how to keep them cold. They sent big packages of coolant with some of the original space telescopes, and it didn't work out for them. The coolants would evaporate, they would leak. They actually had a serious problem with one of the infrared instruments on the Spitzer Space Telescope, which was launched in 2003. And so the new technology seems to be looking primarily into ways to sun shield these things. That is, just keep them from getting hot in the first place. And so the passive cooling systems will be like a huge frontier. If any of you are into engineering, these are hot topics that need to be developed. And there's actually a lot of resources and money being devoted to this. You know, why is space travel? Well, you know, there's a lot of interest in going to the moon right now. There's a lot of interest in going to asteroids, and a lot of this is motivated industrially. I mean, the amount of precious metals available on a single asteroid rivals, you know, the output of the globe in a year. It's just incredible if people could find a way to do this. And so naturally, they want to go to the moon to set up bases because the moon doesn't have an appreciable atmosphere. And like I said, the trickiest part of getting into space is punching through the atmosphere. So if you build things on the moon, you basically can just throw them up with some rockets and they'll go into orbit. And you don't have to spend all of this money and energy trying to get your tube full of stuff. You can just have a pallet on the moon, right? You could just take this whole classroom, stick a couple rockets on it, and shoot it into orbit with very little effort because there's no atmosphere, and that's the main problem. So I think we're going to see a lot of industrial processes being moved to the moon in the next century or so, which is pretty crazy. You look horrified. Yeah? Why is that? I mean, I used to think kind of the same thing, but I thought about it a bit, and it makes sense to me that we'd want to keep the Earth as a nice place, you know? This is kind of it's like, you know, if we start it's hard to do any industrial processes on Earth without destroying the place. And so it's like, would you rather have like a nice... It would, but the moon is already, it doesn't have a forest to destroy. That's the question, right? Yeah, yeah. It's going to be, it will definitely be a game changer when there's city lights on the moon at night, It's going to be different. What's up? The diameter, yeah. Yeah. There's also the far side of the moon, right? Which is an option. It's something to think about. I've talked to a few of these people who are actively raising money to do asteroid mining, and they have persuasive environmental arguments for why industrial manufacturing should be happening in space. Space has one of the most costly aspects actually of doing industrial manufacturing is the production of vacuum, and it turns out there's vacuum everywhere in space. But the cost of modernity seems to be a lot of bad chemicals get made, and people don't seem in any hurry to stop making chemicals. And like I said, everything in this room was made with industrial techniques that required, I'm sure, all sorts of terrible pollutants to be extruded somewhere, and we don't really have a great place to put pollutants on Earth right now. We bury things in the side of mountains. This is kind of the best thing we can come up with. And space seems to be vast, It's a conundrum. Obviously, we'd want to minimize our impact, but the question really becomes, do you want to keep Earth clean, or do you want to keep everything else clean? Something to think about. It's something to keep an eye on, This isn't quite happening yet. I don't know how long it will take them. They keep moving the dates back, we spent... if you look at the budget that was spent on getting to the moon in the 70s, it's just unbelievable compared to what's available, at least from the state-funded projects today. And that's why you see these partnerships with corporations like what Elon Musk is doing. They can just raise more money. And so this opens up a much bigger conversation about how we fund things on Earth, right? Because we're definitely tending in our society now towards a very corporate-funded regime where there's private exploration of space, and as long as people don't want to pay taxes for space exploration, then it's going to continue to be that way. Me personally? So it's tricky. So ideally, like the entire government functions something like a corporation where, you have people who are actually people are able to actually be the board of the corporation and weigh in on it. So to the extent that that's a functional system and we're actually able to keep control over the corporation itself, it seems like it's an idealized system. And I think this is something like what the constitutional founders imagined. Unfortunately, it doesn't always play out that way, right? There's people always questioning whether voting makes a difference, whether the politicians are just going to go to Washington and do what their investors have told them to do, the big money investors. And there's a lot of corruptions like that certainly need to be addressed by the next generation. And so I think to the extent that those conflicts of interest are able to be addressed, that the privately funded space, the privately funded space industry is fine. It needs to be obviously kept in check by the human beings. Corporations aren't human beings, which makes them a very strange person, because they're treated like a person under the law, but they don't have human interests, right? Like a corporation, doesn't really care if it pollutes a river, right? Because it doesn't live next to the river and fish in the river. And honestly, it's an amalgamation of people's financial interests all over the world, right? I might own stock in a corporation that has a factory, on the other side of the earth, and so I'm not capable of really weighing in those costs into my decision of whether I want to, continue to fund this corporate project. So this is something that needs ironed out. And I can't tell you that it will be ironed out, but hopefully it will be ironed out. Hopefully we'll get some smart people into the different, not smart only, but compassionate people who are aware of this problem, who will make their way into the judicial system, into the legislation, and we can correct this before it becomes a complete dystopian nightmare. Which it isn't yet, and it's really worth mentioning that we have far less war on the planet than ever before today. We're not really living in a dystopian nightmare right now, but these non-human actors do have a lot of power, and that does make one nervous about what could happen. So, long-winded story to say that I think that the real solution is actually in getting a human control over the events that happen on Earth, and not just letting the autonomous, profit-driven structures pull that off, because they're basically computer programs. I don't know if any of you have played with the stock market at all, or you have index funds or something. Maybe you should start a retirement fund, whatever. But a lot of these work autonomously. Index funds simply take your money and they invest it in the corporations that are doing the best. That's just an algorithmic-driven process. So the corporations that are doing the best are the ones that get funded. That doesn't necessarily mean they're the ones that are doing the most humane things for the world, right? But if you don't want your money to just depreciate due to inflation, you better invest in them. And so it's this meta phenomenon that isn't necessarily motivated by individual human decisions at some point. And so the government and the people can actually do a great service by regulating those corporations, because they can't regulate themselves. They can only make money. That's what they're designed to do. And that's not a bad thing, but they're not going to certainly come up with rules that are going to take care of the place and keep us from getting poisoned and make sure that we have fish in our river and stuff like that. Okay, way off topic. Sorry, guys. All right. So this is a really cool picture. I want to move in and start talking about the solar system. If we don't finish today with it, that's fine. We'll finish up next time. This is a really beautiful illustration from National Geographic from a few years back. It's a little bit out of date. I posted a link to it in Moodle in case you want to zoom in on it and check it out. But these are essentially, this is a picture of how the humans have begun branching out into the solar system from their home. I'm going to turn down that light just a little bit. But it really gives you a sense of the Earth being almost it almost looks organic, It almost looks like the way you would expect a bacterial colony to fill up a dish or something like this. There's something, this is all anecdote. This is all analogy to some extent. I don't think it's fair to treat the Earth as a single organism necessarily, although some people would argue that it should be. But you can really start to see that we're making our way around this place, and we're really starting to explore and really leave our footprints on these places, which can be done responsibly. It can be done very irresponsibly too. And so, just looking at this, we've had several far-reaching probes like Voyager and Pioneer, and we've landed on, we've touched Jupiter's atmosphere. We've been on the surface of Venus and Mars and the Moon. Been to some of Saturn's moons, asteroids. We've been to comets, and so this has all pretty much happened. This, as of the date of this, I think it was like the last 50 years, but I think in the last 70 years or so, all of this has happened, which is quite remarkable, which means that our understanding of the solar system has been updated wildly too, because, at the end of the lecture, I want to talk about the different theories for the origin of the solar system. Most of them were developed without having a single piece of hard evidence of anything other than what's on the planet. So they're just looking out, trying to make stories up. Intelligent stories, but still stories nonetheless. And so the ability to visit these places has allowed us to bring back samples and construct dating regimes and imagine the procession of events that led to what we see today. I think we're quite a long ways away from understanding what we see today, but we'll get into the various stories that that we have at the moment. So let's just start at the interior and work our way outward. We have, this everything that we've ever dated in the solar system seems to cut off hard at this 4.5 billion year mark. And so it's generally written, and it's written in your textbook, and most people are under the impression that the solar system itself is about 4.5 billion years old, which is a very long time. I'm not sure that it's correct, because as we'll see when we study the dating system in a bit, all we can see really in terms of dates is the last time that the surface of these rocks was melted down, right? So if for whatever reason the surfaces of planets and asteroids are getting cooked off every few, let's say 4.5 billion years, then that's as far as we're going to be able to see with our dating clocks. So that's something really to keep in mind as we go through this. And you see this over and over in science, and it's not a bad thing, but science is extremely conservative. It's a skeptical discipline, I believe it was Feynman, a famous physicist and lecturer, who said that, science is a discipline of skepticism. Religion is a discipline of belief and faith, right? And so we try to have as little faith in our own theories as possible, because this keeps our minds open to the idea that, there's probably a better way to frame things. It's a progressive discipline, which is pretty cool, because you don't see that so much in other disciplines. It's very rare that people are going to rewrite the history books or the literary interpretations. So these are our interior planets. We call these the terrestrial planets. They're very rocky. And that constitutes Mercury, Venus, Mars. And then beyond that, we have an asteroid belt and then Jupiter and Saturn. We'll go through those in a second. The gassy giants, it's funny that they're called gassy giants because the molecules inside of them are actually so compressed that they're much more like liquid planets. And that's probably a more reasonable way to think about them. We talked a little bit about the sun last time. The sun also suffers from this misconception as being a burning ball of gas, but again, it's under a tremendous amount of pressure. And of course, it's electrically active too, which puts it in this strange realm of plasma. And plasma can be thought of as, we talked earlier about these ions in space, right? Plasma is kind of a similar phenomena where you are essentially metallizing these molecules. Their electron shells are bleeding together into one. And I think something similar is happening on the sun. It's considered a plasma. It's a liquid-like plasma, though, right? It's not a gaseous plasma. And so we have to start to think about what the actual structures of these bodies are. So gas giants, more like liquid giants. We'll talk about those in a second. And then beyond the gas giants, there's this whole series of little bodies out in the Kuiper belt, is what it's called. And they're also referred to as trans-Neptune objects. And this includes Pluto, which has been on and off considered a planet. Turns out there's others that rival it, so they demoted it to, what is it called? It's it's escaping me now. It's a provisional planet of some sort. A dwarf planet, there you go. Okay, so where is all of the material in our solar system? Well, it seems like most of it, the overwhelming majority of the material is in the sun. And the rest of it is in Jupiter. And then a tiny, tiny, tiny little bit of it is in everything else. And this is central to our story, particularly because, in the course of developing this solar system, when we start to theorize about how this happened, we have to try to rectify two really confusing aspects. One is that all of the mass is in the sun, but if we take the extant model, and really the one that was developed by Laplace in the 1700s, that there's a big disk of material that's swirling around, and then it basically tightens up and makes the sun. Well, the sun in that model, when it starts out, is spinning really, really fast, right? Remember, as the figure skater contracts their arms, they begin spinning faster, right? This is the conservation of angular momentum. Now, what's really puzzling and disconcerting to astronomers for hundreds of years is that while the sun has all of the mass, it has almost none of the angular momentum. And this is a real nightmare to figure out. And most of our theories of how the solar system formed come down to ways to explain the fact that all of the angular momentum is in Jupiter, actually. You know, it's turning quite fast, actually. And the sun is hardly turning at all. This doesn't make a ton of sense at the outset when you consider a spinning nebula that's collapsing down. And so we're going to look at all the different mechanisms that people have come up with to rescue that phenomenon. It's still an open topic, for sure, known as the angular momentum problem. We'll get into that some more. Hopefully we'll have time. All right, so I want to talk just a minute, too, about densities. I think there might be 1 or 2 quiz questions about density. So remember, the density is just the amount of material. We can qualify that as mass, right, from a gravitational standpoint, per volume. And so the equation for the volume of a sphere is lifted up there. That we treat these all as spheres. You know, for the most part, they are. But what's really interesting is that the most dense bodies are interior. They're these rocky metallic things like the one we're standing on. And they're actually something like 4 times, like the Earth is something like close to 4 times as dense as the sun, which is a bit puzzling if you think about, you know, the gravitational collapse model of this nebula, this accretion model that we have for the solar system. You know, you might think that's very strange. The sun has a density of like 1.41. Water is about 1. The Earth is somewhere in the 5 range, and you're like, how does the sun have less density than the little bodies that are around it? And the argument is made that the core of the sun is actually quite dense. I think that it's in the, oh, nice, I made a slide for this. So here's the density curve for the sun. You can see over at the left is the core of the sun, and over at the right is the atmosphere. And as we get out into the atmosphere, the density drops down. It has quite a large atmosphere that actually extends for millions of miles in some cases, which you can see during the eclipse. It's called the corona. And so if you average all this out, even though you have a density like something like in the 20 range over here on the left, you, wow, even more than that, right? Let's see. 10 squared, so 100 grams per centimeter cubed. Over at the core, as it stretches out, you get this depreciation of the density, and overall, it averages out. So there is a lot of really dense stuff at the center of the sun, and this helps us understand. Now, in terms of how the rocky bodies formed and became so dense, there's a number of ideas about that are all in competition, and we'll talk about them a bit later. Right, so these are our terrestrial planets. We have Mercury, Venus, Earth, the Moon, and Mars. The Moon's considered a terrestrial, but it's not considered a planet because it doesn't orbit the sun directly. But for all intents and purposes, its composition is very similar. We cluster it in with the rest of these. Most of these are made out of rocks and metal, which is quite a bit different than the liquid gas planets. We'll talk about those in a second. Mercury actually has the most metal, which are quite dense, and the Moon has the least amount of metal. But they're all roughly the same. About a third of their mass comes from iron-nickel or iron-sulfur combinations, and then 2/3 of it's made out of silicon, and particularly oxidized silicon. This is actually quite important to the establishment of life, because the chemistry on these planets is said to be oxidizing chemistry. That simply means that there's a lot of oxygen bound up in compounds, whereas we'll see with some of the other gassy keep wanting to call them gassy, but they're really liquid planets. Their chemistry is reducing, so we see the presence of more charged species. And so this is, I think, really instrumental into not only looking for life, but thinking about what life will be like on other planets. I've been talking to a lot of people who are looking for life on other planets. And I've written a bit about it in some different magazines too. It's quite an interesting endeavor, because on one hand, you want to look for something that seems similar to what we would see on Earth. But there's a compelling argument to be made that if there's life on other planets, it might look nothing like Earth, because it might have developed to deal with a completely different set of chemistries. And so there's some really fascinating discussion about what is life and how do we find it. These are all more or less similar. Venus is kind of a strange example. It has a really thick atmosphere, predominantly carbon dioxide, which insulates it, sort of like the greenhouse effect here on Earth, and it keeps the surface temperature of Venus really, really warm. Venus also barely rotates. Venus is also really strange because it rotates the wrong direction. It's called retrograde. This is a real problem for the nebular collapse hypothesis, because it's not totally clear how you would transfer angular momentum to something like all of your angular momentum of your star. All of the spin gets transferred to Jupiter somehow, but Venus somehow not only got left out of that exchange, but it's rotating the wrong way. And actually, we see a lot of different bodies, especially moons, as we move outward, that are rotating opposite even other moons at the same planet. And those are thought to be captured. And so there's been a historic debate about, you can roughly group the ideas about the solar system formation into, okay, everything formed in place, or everything was captured at different times. And people argued about this over the years. For the most part, at least in the last, up to about 10 years ago, everyone thought that the planets formed in place. After they resolved to stick with this nebular hypothesis, they thought that everything formed in place. But very recently, the last 10 years or so, they've been finding what they call hot Jupiters, which are these big gas, liquid giant planets that are very close to their suns. And this really opens a can of worms as to how those planets might evolve over time, how they might have their atmospheres blown off and turn into something else. Maybe they evolve down into something that looks a little more like Venus or even like the Earth at some point. So these are really interesting hypotheses. I prepared some slides. I don't know if we'll get to them, but that's a really fascinating hypothesis. All right, so then there's something else that's kind of interesting about these rocky planets. They have these cores to them, and one of the hallmark features about our planet, which distinguishes it from the other Rockies, is it has this really strong magnetic field. And what is a field, first of all? Well, field is essentially just a mathematical way of saying that there's some sort of activity happening that's varying from position to position. And so we can think about this as the way that the atoms are moving in this electrical fashion, and their orthogonal component is that magnetism. And what it has the effect of doing is throwing off incoming particles that are high energy. So the sun is constantly spewing out ionized material, right? It's essentially evaporating at the surface, and it's kicking off all of these particles, little hydrogens and heliums, essentially. And they're flying off, and if we didn't have this magnetic field to deflect them, if we didn't have this magnetic phenomena that was cohesive with our planet, we would be constantly bombarded with these very fast-moving particles, which would just destroy everything. And so Venus doesn't have an appreciable magnetic field, and it's very strange that it doesn't, because it's thought that its structure, it's thought that it does actually have a core. And the question becomes, how is our own magnetic field even generated in the first place, which is a bit beyond the scope of this lecture. But it has to do with the particular motion of that core with respect to the outside of the planet. And so in order for this process, which they call the dynamo that generates our magnetic field, in order for that dynamo to persist, you have to have venting, is the thought. The thought is that there's convection, which means essentially that there's this motion due to heat escaping from the core. And we have all these vents on Earth, and we have plates, and there's big rifts in between the plates. And it's thought that this motion of the heat from the interior outward causes this churning of the core, which is able to generate our field. Venus doesn't have those cracks on it, actually. It doesn't have the same cohesive way for heat to escape. And so it doesn't have a magnetic field, and obviously it seems to have suffered the fate of that as well. It's a very unfriendly place to go to. Actually, I think we've just recently made it down to it. I think the Russians actually put a spacecraft on it recently and took some interesting pictures. But it's hundreds of degrees on the surface. It's a very unfriendly place. And you know, that idea of how the magnetic field is generated is also a very open topic. If anybody wants to sink their teeth into it, there are theories and they have their flaws. So what else shall we say? All right, let's move on from. This is Mars. Mars is also suffering from a similar predicament. You know, some people believe that Mars once had more venting, and hence that it had. You know, there's reason to believe that it did have some magnetic field activity in the past. You can actually look at the rocks and see how they're magnetized at different ages. And it seems like very, very long ago, like 4 billion years ago, Mars may have had some magnetic activity. And perhaps like the surface has been remodeled. Perhaps it had plates. Perhaps it had venting that was able to sustain that dynamo. We don't know. So when we move past Mars, something really interesting happens. There's this big field of debris, which is called the asteroid belt. And you know, the provenance of the asteroid belt has been up for debate over the years. It very much looks like something just blew up and got stuck there. There's issues with that model, though. Today, it's more or less considered to be left over from the formation of the solar system itself. And, you know, it may be so. Certainly, many people believe that it is so. The problem is that if there was a large planet that was destroyed, that was out there, it wasn't very big, or it's missing. The rest of it is missing because the asteroid belt only has something like, let's see, it only has 4% of the mass of our own moon out there. So it's very thinned out, and there's not much material left over. So it's hard for people to explain how something big would have gotten blown up and left behind there. Some of the asteroids actually look a lot more like moons than they do like asteroids. There's a couple of them: Ceres, Pallas, Vesta, and here's a picture of them. This is oh shoot, I didn't write down which is which. Okay, this is Ceres next to our moon there, and then on the left is Vesta, which is another one of these large asteroids. You know, and there's some thought that maybe Ceres could have been a captured moon that lost its orbit and ended up out there as well. It's difficult to, you know, in order to have something that's spherical, you need to have a great deal of gravity that's able to pull all of its sides into perfect alignment and get a sphere. And some of these little spherical bodies really test the limit of the ability to establish that equilibrium that's necessary to make a spherical object. And so they very well may have longer stories than we're aware of. Like I said, a lot of the stories we tell about this are constrained by this 4.5 billion year hard stop. And so when we're trying to explain how things happen, we don't really want to say anything happened before 4.5 billion years ago because we don't have evidence of that, right? That's not to say it didn't happen, it's just that we can't say that it happened. And so it really constrains our imagination of how these things formed. Now, if it turns out that we're able to either understand the limitations of that in a concise way, or we find something that's dated older, and then we might have new stories about how some of these objects formed. Maybe they've just evolved over gazillions of years, and they used to be much larger, and that's why they're spherical, which is an interesting blind spot in the whole story. We think that there's some meteors actually that have landed on Earth that we think are actually parts of Vesta because they're compositionally so similar. This may be the case, or it may be that that's a very common sort of body that's out there, and we just periodically run into pieces of it. All right, let's move on. So we go past the asteroid belt, and we come across the Jovians. This is our name for the class of liquid gas objects. So see Jupiter, Saturn, Uranus, and Neptune. And they're quite large, so about 1,300 Earths could fit inside of Jupiter. And what's really interesting too is that Jupiter seems to be, and the other, well, we'll get to that in a second. So they seem to be very compositionally similar to the Sun, which opens up a whole can of worms about the difference between a star and a planet like Jupiter, because they're actually not that different. There's a gentleman at UC Berkeley that I had a chance to talk to named Gabor Basri, and he studies these brown dwarfs, and he really thinks of them as failed stars. Like they went through the same process that we would go through to make a star, and we have a whole piece in this course talking about how stars are made, so I won't do it today. But maybe if there's not enough, not the right perfect conditions to cook a star, you end up with something that looks a lot like a Jupiter sometimes. And there's now thinking that there might be lots of these out there just drifting in interstellar space, collecting even in the Oort cloud, right at the edge of our own solar system, that are essentially failed stars. And, this also has figured heavily into the whole capture hypothesis with regard to where all these planets came from. There's difficulties with that too, because the planets are all very nicely stabilized in their orbits. They don't have wild eccentricities. They're not crashing into one another all of the time. And so folks have a hard time assimilating capture hypotheses because they can't figure out how it would have stabilized in such a short amount of time. 4.5 billion years seems like a long time, but it's really not when you're trying to stabilize a huge object in a gravitational orbit, which is rather weak. Again, if that 4.5 deadline extends, then maybe we're looking at different stories altogether. There's something really beautiful that happens actually in these orbits, which we didn't get to talk about too much. These are the moons, 3 of the moons of Jupiter, and they're in this very beautiful resonance. And I know a lot of you are musicians out there, and certainly the early astronomers were obsessed with this. They saw music in the way that these bodies moved because the ratios at which they orbit tend to resonate with one another. And what is resonance? Well, it's just this idea that a periodic impulse will help along another object's periodic rotation or vibration. And so 3 of the moons are actually in these very perfect resonance ratios with one another. Io orbits turns once per every Jupiter rotation, and so on. You can see the rest of these. These are actually, there's a perfect octave there, which is 2-to-1, and then 2 octaves, which is 4-to-1. Actually, Venus and Earth are in a perfect fifth. If you play music, that's a very nice interval. It's kind of your standard major chord for the most part. So there's a lot of music going on out there, and the ancients were obsessed with this. They thought this was like a sign that it was all put there by God. But I think that it's probably equally as meaningful to realize that music is something which is there before humans get here. The animals are very capable of making music as well. When I was a grad student, there was I knew a lady who had a lab, and she had found that she was studying these frogs and how the mating calls between them. And one of her grad students noticed that the frogs actually were singing these perfect intervals. They were singing like perfect thirds and perfect fifths. She had like perfect pitch. This girl was also a music, quite a musician as well. I think she had done her undergraduate in music studies and moved into science. And she noticed that the animals were actually doing these perfect intervals as well. So music seems to be quite foundational to existence in general because it's essentially a resonance that occurs. This is just, quite mind-bending. And you see these all throughout the cosmos. All the other planetary systems have beautiful resonance systems. And they're the intervals that we also find pleasant to listen to. It's just kind of mind-bending. It's quite interesting. So the one that's left out of this, by the way, is Callisto, who was our nymph from our story about the bear, the constellation Ursa's. Callisto does not participate in this resonance, which is very bizarre also because, again, it makes you really think about capture theories, about how these orbits change over time. I think there's this tendency in science in general, but particularly in astronomy and particularly in cosmology, to really, actually in geology as well, to be really conservative about how things change over time. We really desperately want to say that everything is perfectly stable and things don't change, and this is how it's been since it was formed. And I think there's like a deep psychological root for why we do that. I think part of it is because we're deeply skeptical as scientists and we don't want to overstep and make theories for things that we can't observe evidence for directly, despite how tempting it might be. But there's also something about the safety that we want to tell in these stories to ourselves about the stability of the world that we live in and how it doesn't change that much. But it seems increasingly obvious that as the solar system formed, things were rearranging quite a bit. Maybe they rearrange to this day. Maybe things can happen. These are very, very precarious balances of forward momentum and the inward pull of gravity. And they're very subject to one another's interactions. And so, I think most scientists will admit that it's very difficult to predict the stability of these beyond a certain range of time. And that seems to be a fine range of time. We have like some sense of stability of these resonances amongst the planets over the next, say, billion years or so, which should be plenty of time to sort things out. But beyond that, it's really anyone's guess as to whether the eccentricities will develop to the point that Venus is crashing into the Earth or completely abandons her orbit altogether and leaves the solar system. The same goes with the moon. We talked about that before. So the composition of these, like I said, is quite fascinating. And we talked about this a bit, but the Jupiter and Saturn are very similar in chemistry to the Sun. They're mostly hydrogen, about 75%, and about 25% helium. What else should we say about these today? We're going to do a whole lecture on the gas/liquid giants, so we don't need to get into too much detail right this moment. Ring structures. We also have a whole section devoted to ring structures, so there's no need to get into too much detail about that. The story of the rings, we're looking at Saturn here, actually Saturn in eclipse, which is why it looks so beautiful. The sun's on the other side. There's actually no real consensus about how the rings formed, which is quite fascinating. I know there was a big pop-sci hit this year about some scientists had proved that there was actually a destroyed moon that became these rings. It's far from consensus view. People don't really know. But we do know that the rings are a particulate system comprised primarily of water ice, and there's a bit of rocks there as well. So we'll discuss the details of that more. And we've had a very recent spacecraft out there called Cassini. It's given us a lot of information. The rings are also in a beautiful resonance with one another. You can see all the different notes of the scale that are played out by their individual resonances with one another, which is just, kind of mind-bending. Saturn also has quite a tilt, and so just like us, it's tilted at, I think, closer to 27 degrees. And depending on where we're at in our own orbit around the sun, we'll get different views of Saturn. And this makes it very easy sometimes to see the rings and almost impossible at other times. Saturn takes something like close to 30 years to go around the sun. And so we're much more likely to see the tilt based on our position than based on Saturn's position. Saturn has also some really crazy orbits for its moons. Some of them are going backwards, some of them are going forwards. Many of them are not in the plane of the, of the equator with the rings. This is very strange too, which again, more curiosity about how these formed and if it's picking up moons still and what's exactly happening. There's a big dust cloud out there, so this tiny little dot at the center is Saturn, and there's this huge dust ring as well, which doesn't entirely appear to be equatorial, which is strange also. So I think what I'm really trying to impress upon you with this is just that there's a great diversity of motions and arrangements inside of the solar system. And none of them really easily lend themselves to this uniformitarian perspective that everything just started exactly as it was. And the only reason that we have this uniformitarian perspective is because we can't say for certain what exactly did happen. So, all right, so we move beyond Neptune, and we have all these little guys, these dwarfs, of which Pluto is perhaps the most famous. And Pluto has a number of moons which are also orbiting in very strange patterns. And we call these dwarf planets. They're actually they're very similar in composition to a lot of the moons of the gassy liquid giants. They're rocky and icy. Some of them have higher density than others. And there's discussions about where they come from. You know, some of them have been thought to be accretions of comets. Some of them are thought to be captured moons. They're very diverse. And here's actually a spread of all of those little bodies. I mean, there's gazillions of them. I think this is partially why Pluto lost its status, because there's just so many of these, and some of them rival Pluto in size. So a little look at Pluto too. It seems to be mostly rock with a big layer of ice on top of it. And actually these little red spots are just dirt that's appeared on top of the ice. Very strange and alien and lonesome worlds, very cold. You know, Pluto's temperature is something like 10 times less than Mercury. It's very cold out there, whereas Mercury's quite hot. So then it's probably worth mentioning comets and meteors, because they're often confused. Comets are thought to originate way beyond the trans-Neptune objects, all the way out at the Oort cloud, right? And periodically, the comets are on these very eccentric orbits, and they make their pass by the sun. You know, they're thought to have been destabilized by something essentially interacting with our outermost shell, this Oort cloud, which sends them careening in towards the sun, and we get this very beautiful display periodically. I hope we have a chance to observe one soon. The difference, okay, so it's worth mentioning, comets are thought to be icy, meteors are thought to be rocky, and a meteor is actually this burning up thing that you see flying through the atmosphere. Once it's landed on the ground, it's called a meteorite. Worth a little bit of trivia there. That's you know, people always correct you. I didn't have this right for a while, and I would talk to people who would always be correcting me about meteors and meteorites. The right is the little thing that you find on the ground. All right, so let's talk with the last 10 minutes about dating, because I think, and a little bit more about the different origin stories for this place. Maybe we can start next time, because I probably won't be able to get through all of them. But historically, when we were trying to gauge how old things were, we would look at the craters. You know, things that were more cratered were thought to be older. As soon as we went to the moon, or really, and Mars, and so on and so forth, we started to establish that the dates were actually quite similar for all of these things. And so something else must have been going on. It turns out that the craters are really, all we can say is that the amount of craters tells us how long it's been since the surface was remodeled. And I think this is going to be an increasingly important concept in planetary science is that the surfaces of planets do get periodically remodeled. You know, we talked about our own moon and the formation of it being, at this point, very recently now, thought of as an impact event, which completely remodeled the surface of the Earth. You know, I was talking to this guy over the weekend for our podcast. His name's Chris Kirkland. He's in Western Australia at Curtin University. And he dates these very old rocks. Like, that's his job, is he does these spectral analysis, these mass spec analyses, and creates these isochrone plots to get the dates. And you know, he pointed out that there's very few old rocks left on Earth. You know, the surface is being constantly remodeled. There's actually, I think, only one or two really old rocks, and they're basically found. There's one in Western Australia, and there's one in Greenland. And it's very difficult to look back in time because it's very difficult to find a place where the surface hasn't been completely redone, either by internal processes like tectonics, activity of the plate, or from impacts. Right? When you got hit by the moon, vaporized everything, melted everything. That was it. So what people are relying on mostly is this dating process, which I've hinted at a little bit. And the basic idea is that there's naturally occurring radioactive elements all throughout the cosmos. And they can be found in relative abundance in our rocks here on Earth. And the idea is that radioactive elements fall apart into constituent pieces at a very predictable rate. And so we call this the half-life, which is essentially the amount of time it takes for half the material to have degenerated. And by looking for the ratio of the degenerate product to the parent, you can start to set up these plots. And so here's a few of the different elements that we use as clocks. You know, you can see the parents there. In this case, like uranium, it decays into lead. So uranium-238 decays into lead-206, which actually coincidentally has a half-life of about 4.5 billion years, which is a very strange coincidence. But what happens is when you take a rock, you can find these little crystals of zircon, which are a particular arrangement that embeds, that freezes in the chemistry. That is like the amount of parent and daughter at a particular place. And what you can do is you can plot the ratio of parent to daughter on a line, and from that line, you actually do like a basic linear regression. You know, you basically fit an equation to it, and you can pull out the convergence of when these would be expected to have formed. And it's a very internally consistent method because in one of these little tiny crystals, not only do you get, say, this is called an isochron, so this is the line that's fitting it. Not only do you get an isochron that will tell you the age, but you also get isochrons with respect to how the daughters decay into their own products and so on and so forth. So you can actually get multiple controls from the same crystal. You can see different date lines, and they should all converge and give you the same date. If they don't, you know it's not a good rock. Something interesting must have happened, like maybe some of the lead got into the crystal after it was formed or something like this. And so the main problem with this kind of dating, again, is that it can only tell you the age of that crystal at the time that it was last melted. And again, this is where we get all of our dates from. You know, this is going to be impossible to do in 2 minutes. So why don't we start next time with a historic overview of the different solar system formation processes. And we'll leave it at that for today. It's too important to just try to blast through it. If anybody has questions, come see me afterwards. And yeah, we'll see you next week. Thank you, guys.